gas, we're going to use as our main equation the ideal gas law. So this is called the ideal gas law. Can I just have a show of hands? How many people have seen this before? Okay, good. So I don't have to go through it in that much detail. It's an excellent approximation to modeling a gas that's not too dense. It's fairly dilute. You can actually derive it from first principles using physics 1 techniques by just assuming you have a bunch of independent particles colliding with the walls of a container. It's assuming the gas particles are all independent. Let me quickly just write down. This is the pressure of a gas. We usually do that in pascals. This is the volume the gas occupies in meters cubed. N is the number of moles. So a mole is a convenient grouping of large amount of stuff. Okay. So you may know that 1 mole of things is 6.02 times 10 to the 23rd things. Okay. So you can use it for anything you want, but obviously with atoms you have more need for talking about a very large number of things. Okay, so that's what 1 mole is. In our case, we're talking about particles, gas particles. Okay. So for moles, I use lowercase n, and that's distinguished from n, which is the number of particles themselves. Okay. So you can talk in either language, but of course, it's more often makes sense to keep the numbers down to a reasonable size to talk of moles of things instead of these gigantic numbers of actual particles. So you can take the particles per mole, and of course you'll always end up with Avogadro's number, which is this thing, 6.023 times 10 to the 23rd thing particles per mole. Okay. So no matter what your sample is, if you divide the number of particles you actually have by the number of moles you actually have, you'll get the same number. That's just a definitional thing for moles. So over here, let's just make a little conversion chart. Here we have moles, here we have actual particles. The conversion factor between them is what I just wrote. So the two variables, if you have one, you can always get the other because they just relate by a constant. Okay? Then what else do we have? We have the temperature. Now this is T, not delta T, so this has to be in Kelvin. Okay? And then R is what we call the gas constant. Is that what you guys call it? Universal gas constant. That's 8.31 joules per mole Kelvin. Okay. So that basically says for a gas, if you have a fixed number of moles, so the lowercase n is fixed, there's an interplay between pressure, volume, and temperature. So this is worth a quick run through, even if this may be old hat. So let's assume we have a fixed number of moles. So we have a enclosed container of some sort. So a fixed n. And then let's let each of the other properties of the gas take a turn being constant. For instance, let's say we have constant volume. Okay. So now our container is rigid. So we have a fixed number of moles inside a rigid container which can't change its size. And the equation tells us that P is proportional to T. Okay? So it tells us that if we heat it up and increase the temperature, that there will be larger pressure, which again, hopefully isn't a surprise. If you have a closed container like a pressure cooker, you heat it up, it goes to higher pressure. We could sketch this, P versus T, and we would get a graph which is linear, which its slope would be nr over v. Okay, so that's just putting this into point slope form. Okay, so if you want, you can write it on the side. Solving the ideal gas law like this would be the y-axis, this would be the x-axis, and then the slope would be nr over v. This itself gets a name, Guy-Lussac's law. That's just for historical reasons, because of course a bunch of people figured out a bunch of different laws before they realized they were all different sides of the ideal gas law, and so we kind of acknowledge that while realizing that they're all just manifestations of the ideal gas law. So that's one example. This graph right here, by the way, is what you'll be doing in lab this week. So you guys will be plotting the pressure versus temperature of gas inside a closed container. And what you'll actually be doing with this is extrapolating the value of absolute zero from this. Okay? So that right there, if you want to label it, that's exactly what you'll be doing in your lab this week. All right, let's like another variable take a turn being constant. I guess let's go ahead and let the pressure be constant. So if the pressure is constant, it tells us that the volume is proportional to the temperature. So it tells us that if we increase the temperature, and we don't want to let the pressure build up, we're going to have to let this gas occupy a larger volume. So if this is the original volume, and then it gets hotter, it's going to have to go to a larger volume. Okay? So if hopefully again, this is not breaking news. Okay, you increase a gas's temperature, and it will either increase pressure if you confine it to a space, or if you don't want it to increase pressure, you have to let it occupy a large volume. So you can also plot volume versus temperature. Again, you get a linear graph, and the slope of that is nr over p. So same type of thinking. This is called Charles' law. Again, it's just one aspect of the ideal gas law. And finally, let's let the final variable take a turn being constant. We have constant temperature. So this one is a little bit tricky. You can see that P is proportional to 1 over V. So this is not expected to be a linear relationship if I plot P versus V. If I plot the pressure versus volume, it will not be linear. So what you see is that if I increase the volume of the gas, the pressure is going to drop. Okay? And this is your classic kind of y equals 1 over x look to it. And because we're talking about constant temperature, this is called an isotherm. So along that line, the temperature of the gas doesn't change. I guess I got to tell you its name here. This is called Boyle's law. Again, the names of the laws aren't important. They're really just different aspects of the ideal gas law. But if you've heard of some of these laws in other classes, then you kind of know what you can kind of have that connective tissue to things you may have heard of. So that's your isotherm. And of course, where everywhere along this line, nRT is constant, but if your temperature was higher, then it would shift this. So if this is a temperature isotherm for T1, some temperature T1, if you had another temperature that was higher, it would also have the same look, but it would be shifted higher. So that would be the T2 isotherm. So that would be if you had a temperature T2 that you wanted to maintain while you looked at the pressure-volume relationship. This graph is perhaps going to be the most important of our graphs out of these three, because the area under the curve is going to be a meaningful physical quantity. So the area under the curve here, as I will show you, I guess I'll spoil the punchline right now, but the area under the curve is work. So you may remember physics 1, we talked about work. It's an important quantity. That's what the area under the curve is of a P versus V. In fact, we use so many P versus V graphs that we don't even bother to say the versus because it takes too much time. We say PV graphs. Okay, so this is a PV graph. It's short for P versus V. Okay. So before I move on to talking about the area under the curve and all that stuff, I do want to point out it is possible to phrase the ideal gas law in a way you may not have seen it, where you do talk about the number of particles instead of course, the number of moles. Well, then the constant is different, and it's actually a much more fundamental constant because, of course, a mole is an arbitrary grouping of stuff. This is called Boltzmann's constant. So it plays the same function, except for it's when you're putting into the equation the total number of particles, not just the number of moles of particles. So if the units of the ideal gas constant are joules per mole Kelvin, of course the mole is baked in because you're working with moles, the units of Boltzmann's constant are just joules per kilogram, okay? There's no mole anymore. Okay. Now we can actually figure out what Boltzmann's constant is by pointing out that these are exactly the same two equations, so these two things better be equal. Question?
Do you mean Kelvin or kilogram?
Did I say Kelvin? Kilogram? I meant Kelvin. So joules per mole Kelvin and joules per Kelvin. So basically, over here, I'm just going to say that if you're moving back and forth between the moles and particles picture, PV is proportional to T. That's essentially the essence of the ideal gas law, that those three things relate in that way. But as far as what the proportionality constant is, it depends on what you want to do. If you want to work in moles, then you got to put it in with the ideal gas constant, or if you want to work in terms of total number of particles, then you have to put in that times Boltzmann's constant. Now these have to be equivalent, so if nr is equal to capital Nk, then I can solve for Boltzmann's constant like so. And I can realize that this right here, moles per number, is just the inverse of Avogadro's number. So basically, it's taking the ideal gas constant and dividing out that whole artificial business of the moles thing anyway. Okay? Have any questions on that? Okay, this is something we're going to continue to work on here. We're going to also go to mass in terms of kilograms. We want to be fluid, of course, in any way of describing what we have. What's the mass of stuff we have? What's the number of moles of stuff we have? What's the total number of things we have, period? Okay? So those are the things that you should get comfortable moving back and forth with. I'm not going to do the kilograms part quite yet, but remember that I'm going to add it on probably next lecture or something like that. So there's different ways to describe what you have. So from here, I want to delve further into what we can do with these guys. So let's start with the laws of thermodynamics. Now the first law is going to be, that I'm going to mention, is going to be a little weird. It's the zeroth law of thermodynamics. Yes, this really is a thing, okay? It's the weirdest one, and the reason why it gets a numbering of 0 is because in some ways it's the most fundamental one, but it's the one that they came up with last when they got the numbering of the other ones already all set. So they had to kind of go and shoehorn it in. And so I don't want to sugarcoat that this thing doesn't exist, but I'm going to tell you a little bit of the flavor of it, but then I'm going to come back much later and describe it in more detail. So, one of the things we talked about was heat, right? Heat, Q, is the energy that's in transit from one object to the other. When energy is on the way from one object to the other, we call it heat, right? So, we have one object at T1, we have one object at T2. Let's say T1 is greater than T2. There will be energy in transit, right? So an object doesn't have heat. What an object has is internal energy. So we can talk about the internal energy of both gases. So when they, for some reason, decide that they need to trade that energy, some energy leaves one and goes to the other, then we decide to designate that energy in transit as heat. So internal energy, the one way to state in kind of vague terms the zeroth law is that the internal energy is proportional to the temperature only. That is the only negotiable property of the object that you can use to change its internal energy, is temperature. If something goes to a higher, if a given amount of stuff, so you have whatever, you have, I don't know, 2 kilograms of hydrogen gas or something like that. If you have 2 kilograms of hydrogen gas, the only way that you can increase the internal energy of it is by increasing the temperature. And if you want to decrease the internal energy, you have to decrease the temperature. And I'm telling you that they're directly proportional, okay? So this is proportional to this for a given, I guess, object, for lack of a better word. So I'm going to leave it there. That's enough of what we want to look at for the zeroth law at the moment. We'll come back and we'll see there's a lot of subtlety in this later, but we're not equipped at this point to figure out what else is going on. So for right now, I just want you to take my word for it that if you want to increase the internal energy of a gas, or whatever, it doesn't even have to be a gas, but we're talking about gases right now. So if you want to increase the internal energy, you have to increase the temperature. If you want to decrease the internal energy, you got to decrease the temperature. And, of course, finally, if you don't change the temperature, you don't change the internal energy, okay? That's it. This may not seem like even worth mentioning, but it's going to allow us to push off a lot of the details to later. So, for instance, if we know that if the change in temperature of something is 0, then its internal energy doesn't change, we don't actually have to know the exact function. The proportionality is perfectly fine. It allows us to push off until much later, well, not much later, maybe a couple lectures, what the exact function is that relates internal energy to temperature, okay? So the exact function we'll explore later. Okay, so that's the zeroth law. Again, a little bit weird and unclear what it's good for or how that works. Don't even have a function yet. So now we can move on to the first law. It's an energy conservation law. That's it. So things that are, of course, very fundamentally important in physics, and thermodynamics is no exception. we got to make sure our energy is all accounted for. So we can't just have energy disappear or appear. So let me write down the law and we'll talk through it. Here it is. So here we have some kind of container of gas. And this gas is at a certain temperature, so it has a certain internal energy. And what this equation is saying is that there are two ways that you can change the internal energy of that. Now, one is the method we've been talking about, which is heat. Okay? So obviously, if heat goes in, our sign convention for that is positive if heat goes in. And if you remove some of that energy, take heat out, then Q is negative. So you can see the sign conventions that relate delta E and Q are exactly as expected. If Q is plus, then delta E is plus. You have an increase in energy. You put energy in the form of heat. And likewise, if Q is negative, you've taken energy out. But there is another way that you can manipulate the internal energy of a gas, and that is not by heat flow, it is by work. Okay? So, this is something where we recognize that a gas can easily expand and contract. We're not talking about a solid here. Yes, a solid can expand and contract. We talked about thermal expansion. We've mostly learned that it's a tiny, tiny, tiny effect, except if you have really, really long things like the Bay Bridge. So I'm not including that. But a gas, obviously, it can easily become a larger or smaller volume if I let it. So imagine that this side of the container is like a movable piston. So we know that a gas can exert pressure, and if you exert pressure on something that can move, you can actually have that piston will be pushed away, right? Well, if in physics 1 terms, if you are causing the piston to suddenly pick itself up, or not pick itself up, if you're causing the piston to suddenly accelerate, then that takes energy. So what you've done is, if you've moved a piston or something like that with the gas, then energy has gone to that piston. It came from the gas, right? So the gas passes some of its energy to the external environment as mechanical work, okay? So, let me remind you from physics 1, we had this energy bank account called kinetic energy. And we had these transactions that operated on this. We had positive works that made a deposit on your kinetic energy bank account, and negative works which made withdrawals, right? Does this ring a bell? Talked about work? Okay? So that's exactly what we're doing now, is we're allowing for the fact that the gas might do mechanical work on its environment. So you could have that the piston moves like this. That would represent passing work out to the environment. It's going from the gas to the piston. Or of course, you could do the opposite, where if you push down on the piston and you compress that gas, then you would instead pass energy the other way, from the piston into the gas. Okay? So this is where we have a funky sign convention. Not everybody uses it, but I'm going to use it, and many people do, where the sign convention is actually seemingly backwards from physics 1. Okay? So for us, when energy goes out as work, we call it positive. So when work is positive, energy goes out of the gas. And when work is negative, we put internal energy into the gas. So this is my positive work, this is my negative work. Now you might say, why would you do such a thing? This seems like the worst idea you could possibly think of. Your sign conventions are backwards for Q and for W, right? If Q is positive, energy goes in, but if work is positive, energy goes out. Why would you do that? Okay. Well, first of all, you can see it is built in that this sign convention is built into the equation. That's why this is a minus. Okay, because it makes it so that if the work is plus, then this extra minus will mean that you actually lose energy. And if the work is negative, it means you gain energy. So let me tell you why they do this. It might look like it's backwards from physics 1, but in a certain sense it isn't. Because this might be the kinetic energy of the piston. Okay? Ultimately, the only reason we care about gases is because they do work on the environment, and that's where we care about it. Okay? So if the kinetic energy is going into the piston, it came from the gas. Okay? So, yes, the energy goes out of the gas, but it goes into the environment, which is where we actually care about it. The gas is going to do something for us. That's the only reason we're doing this. We don't care about the gas. We're going to use it as a means to an end to build car engines and things like that. Okay? So yes, it goes out of the gas, but it goes into the environment. And similarly, when it goes into the gas, it actually is going out of the environment, which is really where we care. Okay, it's what the gas does for us. We're not running a charity here. Okay, the gas is just a means to an end. Okay, that is why the sign convention is set up the way it is. Because when energy flows out of the gas, we call that positive work because that's going to mean it's going to go into the very thing we care about. Okay, does that sort of make sense? I swear you'll get used to it. Okay, you will get used to it. Okay? So, so that's the first law. It basically says there's two ways to change the internal energy of a gas. One is by heat, one is by work. Okay? So now, what we're going to do is I'm going to go back to that PV diagram that I had. And I'm going to show you what I already kind of told you the punchline about, which is that there's a significance to the area under the curve. It's work. All right? So let me show you why that is. Okay? So we go back to good old physics 1 stuff. This is, of course, your general expression for work. Does this look familiar, I hope? You haven't completely deleted everything from physics 1 from your brain? Yes? Okay. So, let's take a look at that piston. I'll draw it in a little more detail. So here is some kind of piston. And obviously, if the gas has pressure, we learn that the pressure exerts a force such that the material, in this case gas, wants to expand, so it's going to be an outward pressure. So that's going to be a force on the piston. And if the piston is movable, then we can actually do work. So it'll move slightly. So first of all, at least these are on the same line because the pressure acts perpendicular to the surface. So we can delete the dot product. Okay? Right? It's just F ds cosine of 0. All right? Then the force, of course, is pressure times area. So this is nice where we did the fluids first because we are using some stuff from the early part of the semester. As much as this is a grab bag course, physics doesn't quite work. It's staying completely compartmentalized, so we're kind of using some stuff. And let me, of course, label A. That's the area of my piston. And I guess I should probably draw it again. Once it's moved that ds, that's a bad drawing. Let me try that again. let me just draw the tops, because then my drawing abilities won't be limited, okay? So there is my piston of area A that moves up a distance ds. And I can point out that A times ds is actually the volume here that's swept out. And so this is just dV. So that's the change in volume of the gas. So work is integral of P dV, which is the area under the curve of your pressure versus volume graph. So this right here, if I integrate from V1 to V2, then this will be the work done by the gas on the environment. Okay, this is of course positive area under the curve. So if my pressure versus volume proceeds in this way, that's just arbitrary shape, then the area under the curve is positive. Again, what does that mean? It means that energy is going out of the gas. It's doing work on the environment by going to a larger volume. So that's what I've done here, right? So if this gas is allowed to expand, it's allowed to push the piston up, it's passing energy out of the gas into the environment. Does that make sense? Okay, so this is energy out of the gas to the environment, where we need it. Now, of course, you can go and do a bunch of fun stuff with this. You can say, well, what if I let the gas expand to a larger volume, like I just did, but then, by some other means, let's say I bring it back to the original volume, well then there, I'm going to go to a smaller volume. So I'm going from V2 back to V1. And this would represent negative work. Of course, you guys know that if you reverse the integration bounds, it throws in an extra negative, right? So anytime you're going to a smaller volume, that means that there's something coming in from outside that's making the gas go to a smaller volume. That's, of course, not the way it wants to go. But that's because there's energy being put into the gas by work, and that's coming out of the environment. And finally, we might even talk about this. This is the difference between the positive and negative work that we call the net work. Okay? So that would be the net work. That would be the enclosed area. We're going to do a lot of that. Okay, so we're going to have closed loops on a PV graph, and the enclosed area, which will give us the how much work do we get done overall? Basically, how much did the positive work exceed the negative work, or vice versa? Okay. So enclosed areas are going to be a big topic we're going to look at. Okay. So we do some positive work where energy goes out of the gas, some that comes back in, but not all of it. So we will have a net work in this case that is positive. Okay? So this is positive in this case because there's more positive work than negative work. Okay? Are there any questions on that so far? All right, so we've got the basics of the first law down. Now we're going to look at the various shapes. So how can we move on this PV graph? What do these typical shapes look like? Well, there's 4 different ways in which we normally move on a PV graph. So let's start talking about those. I'll just list them first. isochoric, isobaric. In fact, let me just start a table, okay? So this is the process name. There's a table very similar to this one on your thermo summary sheet. If you haven't picked it up yet, we're moving to definitely past the halfway point in terms of stuff covered on it. So isochoric, isobaric, isothermal, and adiabatic. There are other processes, but these are the main 4 food groups, basically. Okay. So, iso. If you don't know what iso means, it means constant. Okay. So, isothermal is constant temperature. Isobaric, you may remember that bar is one of the units of pressure, so this is constant pressure. Isochoric, I don't know what the root is, but something about volume, because this is a constant volume process. And the adiabatic process is one in which there is no heat flow. So let's go ahead and look at each one of these in turn. And let me actually try to format this the same as on your summary sheet, so it looks the same. We'll talk about the work. I'm going to come in later. There's a heat column here, but I purposely don't want to do that yet, so not yet. I'll fill that in later. We're going to actually punt the conversation about heat in any of these processes for a little bit. We can do a lot without it. What are constants in this process? And when do you use it? So if you're not told it's one of these, how do you identify that it is one of these? So let's make ourselves a little chart. And start filling it in. These are sort of in order of difficulty. So let's start with the isochoric process. So this is a process of constant volume. So we know that a gas can expand, so for some reason the gas is not allowed to expand. Okay, so we have is a box of gas. If there has a piston, someone's put a pin in that piston and not letting it move. And so essentially, you are shutting off the ability of the gas to do work or have work done on it. So you, out of the 2 methods of passing energy into the gas, you've essentially said one of them is not applicable. So what is the work? Nothing. When do you use it? Whenever the volume of the gas is fixed. So essentially, this is what we've been doing with our gases more or less thus far. We have not acknowledged that there's any work at all that's possible. So we have the possibility of putting in heat and having the temperature increase, or having heat flow out and having the temperature decrease. That's all there is to it. You're manipulating the internal energy of the gas only by heat. Now, what would this look like on a graph? Well, on a PV graph, there cannot be any area under the curve, because that would represent work. So it would work like this. It would be a vertical line going up or going down. And in fact, I might want to sketch myself an isotherm. We said isotherms look like this. So if this was T1 and this was T2, I would move from one isotherm to another, but I would do it in a vertical fashion so that there was no area under the curve. So I could either put heat in and move to a higher temperature, so I guess this would be case A, or I could come back the other way. So vertical lines on a PV graph indicate workless processes. Those are called isochoric. Okay? Are there any questions on that? Okay, so as far as other stuff that's constant, we need to go no further than PV equals nRT. Of course, these are always constant, so those are boring. But now we're saying that the volume is constant. So we're holding the volume constant. And so here we said that P was proportional to T. So what that means, of course, is that as you increase the temperature, you go to a higher pressure. It's included here on the PV graph. So notice when I increase the temperature, I'm going from the T1 to the T2 isotherm, I am also increasing the pressure, right? So you can see it here. This temperature is larger, and this pressure is larger, right? So P2 is greater than P1, okay? So you can see it there. Now, as far as figuring out conserved quantities, one of the things I could do is solve for P over T. That's nR over V, which is a constant. So you could say the ratio of P over T is a constant. Or T over P, it doesn't matter. Now, how is this helpful? I guess I can write it like this. I already said it was constant. So P over T, or if you want the other way, that ratio is constant. Now, the way that that will end up being useful in many occasions is like this. If you have a process, you can say that is this kind. You can say P initial over T initial equals P final over T final. This ratio won't change during an isochoric process. Perhaps even more useful is that you rearrange this so the temperatures are on the same side and the pressures are on the same side. Now that's incredibly useful because if in an equation you have the ratio of temperatures, you can replace that with the ratio of the pressures. Okay? So they're interchangeable. That's handy just in a practical sense because if you don't know the ratio of the temperatures, but you do know the ratio of the pressures, guess what? You also know the temperature of both, or the ratio of both. Okay? So you can freely swap one in for the other during this type of process, or let's say you have 1, 2, 3, you can always find the fourth. Okay? So useful things if you know you have one of these. Okay? Is that okay? So that's just different manipulations that you can use. So let's see if we have time for one more, the isobaric process. So the isobaric process. That's one in which the pressure is constant. What does that look like? Well, of course, that must be a horizontal line, since pressure is plotted on the horizontal axis. Now, as far as computing the work, this is nice and easy. The area under the curve here is just a rectangle. So what is work equals integral of P dV? Well, we're lucky enough to be able to factor the pressure out, and then integral of dV is what? Delta V. Right? So there's just your rectangle, right? Height times width. So what's the work done in isobaric process? P delta V. It does have a sign built in, by the way. If, as I have drawn here, the volume increases, then the work will be positive. If the volume decreases, then the work will be negative. So, what are the constants? Well, you kind of do the same thing with the ideal gas law. So PV equals nRT. If P is constant, then N and R are always constant. Basically, the two active ingredients are V and T. So V is proportional to T. Or the way you could think about it as V over T, or if you prefer T over V, are constants. Again, that's useful because you know during one of these processes that you can count on the ratio of V over T to be the same at the beginning as at the end. And again, if you cross multiply here, one of the useful things about this is that you can always replace a ratio of volumes with a ratio of temperatures. So if you happen to have one ratio, you also have the other ratio. If you have three of these, 1, 2, 3, you can easily get the fourth. Okay? All right. So what else can we say about this process? Well, obviously, there's work being done. So let's draw the case where work is going out. But we are also changing temperature. Now, how do I know that? Well, I'm moving from one isotherm to another. I'm just doing it along a different path. So if I'm going to a higher temperature, that means my internal energy of my gas is increasing. Now, how is it possible that the internal energy of my gas is increasing even though I'm passing energy out as work? That can't be true if there's not something else involved. You can't increase the energy of the gas while you're also taking some of the energy out to the environment. So where does the discrepancy get resolved? You're putting in heat. In fact, you're putting in more heat than you are passing out work. So I guess I can draw this as a big arrow. So you're putting in heat. You're passing some of it out as work, but overall you have passed more energy in as heat than you've passed out as work. Therefore, the internal energy of the gas is increasing. Okay? So you have more heat in and less work out. Therefore, you still have the internal energy of the gas increasing. Okay? So, when do you use this process? You use this process for what I will call a medium speed operation. This is when you are able to maintain mechanical equilibrium with the environment, but not thermal equilibrium. Okay? So let me just explain what I mean by that, and then let's knock off. So what I'm saying is this. I have heat going in. That heat would normally increase the pressure. But if this piston is able to move, it quote-unquote relieves that pressure by pushing out the piston. So the mechanical equilibrium, what I mean by that is it maintains this pressure. Okay? So it doesn't let pressure build up because it relieves that pressure. But it's clearly not in thermal equilibrium with the environment because it's going to a higher temperature. Okay, so what we have here, we learned, your whole point of homework 6 was that it's very hard to achieve thermal equilibrium with the environment. It's this exponential thing, it's really hard to get to the same temperature. So thermal equilibrium happens very slowly. So we're pumping in this heat fast enough that, yes, this thing can maintain mechanical equilibrium because the piston can move relatively quickly, but it will climb to a higher temperature than the environment because we're pumping in heat faster than it can cool off. Okay, so I'll come back to this next time. Let's knock off there for the day.